So our next talk is online. It's being delivered by Lena Heng from the University of Prince Edward Island, and he is working with Annabelle Cohen, who is here with us in person. Uh, so we will unmute you in just a second. Good. Sorry. Can you speak, please, Lena?
Yes, can you hear me?
No, we can't hear you just yet.
Um, well, I seem to be unmuted on my side.
Okay, we can.
Okay, is this good now? All right, I guess I'll start then. Okay, good afternoon, everyone. Thank you for having me here today online to talk about automatic note detection and pitch estimation with the MAST 21 and online battery of singing tests. It's going to be something quite different from the rest of the talks we have been having today, I guess. So, singing as a human activity is a form of vocal communication, a complex motor behavior, a form of artistic expression. Singing has been used with success in different therapeutic settings, and it could also be a very useful tool for assessing different aspects of skills, of ability, and control. This could have a wide range of implications, including tracking the development of neuromuscular degenerative conditions or assessing improvements of therapy. Tracking pitch stability, for instance, could provide information about vocal muscular control, and analyzing timbre changes in the singing voice could give indications about physiological and or psychological changes. So with all these advantages, one might wonder why there has not been more tools developed for singing. And one of the biggest challenges for more widespread use of singing for therapy or assessment is how labor intensive it is to convert raw audio data into a format suitable for further analysis. There are numerous pitch estimation, onset detection, and note segmentation algorithms that have been developed, and they have been proven to perform well, and improvements are constantly being made. However, automatically segmenting notes that are sung is much more difficult than doing it on notes that are played by instruments. Note segmentation estimates the onset and offset of the note, which is an important step when it comes to analyzing pitch-related tasks in a singing assessment. Note onset detection tools have used various different approaches. There are energy-based approaches and subband-based approaches, but this underperform when onset energy is weak. Frequency weighting, including peaking algorithms, improves the accuracy, and complex domain methods that integrate phase and energy approaches further improve on previous approaches. Now, here is an example of how automatic note segmentation and pitch detection works. This is the audio file and what the notes should be.
Da 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 da.
So you can hear that, I hope you can hear this clearly, that the pitches are well produced, but this is what is obtained. So you can see that even with this clearly sung excerpt, the notes are not properly detected. There are wrong pitches and there is an inaccurate rhythm. The performance is even worse if the singing is less well produced. So MAS 21 is a battery of tests used to assess singing accuracy, and it's developed based on the AIRS test battery of singing skills. There are 21 trials with the different tasks required for each trial listed here. The test battery is still in development. Different tasks could be introduced to assess other aspects of singing or for different populations. What is important, though, is to be able to automatically segment the notes a participant sings so as to provide accurate pitch estimation. So knowing the position of where the notes are within the entire audio recording can also allow us to assess other aspects of the pitch information, such as pitch stability. Potentially, we are also trying to incorporate timbral analysis, so knowing which portions to analyze is, of course, crucial. MAS 21 is based on an implementation, the Singing Ability Assessment by Sebastian Silas. it has a built-in automatic note segmentation and frequency estimation algorithm, which performs quite well when the singing is well produced. With this test battery potentially being used to test different populations whose singing abilities and vocal control may be more varied, however, we encounter some problems. We found many instances where the automatic algorithm did not detect the right number of notes, meaning in a 3-note trial, for instance, there could only be 2 notes detected, or 4 or 5 notes detected. The problem with this is we're not sure what these errors might be due to. Is it because the participants sang the wrong number of notes in the first place, which in this case, the algorithm is accurate? Or is it that the participants sang the right number of notes, but the algorithm missed some notes out or decided that certain sections are notes that when they are actually not notes? Or the participant did not sing the right number of notes, and the segments that the algorithm decided were notes actually did not correspond to the notes the participant actually sang. So you can see that there are many possible sources of error. Dr. Cohen has presented several models to compensate for these errors at last year's SingWell meeting. However, what those other models do are simply deciding what the best choice of notes detected by the algorithm are. This means that we are still assuming that the actual notes that participants produced are among the notes that the automatic algorithm selected. However, because of the difficulty in accurately segmenting notes, especially for singing that is not well produced, it's possible that none of the 6 notes segmented out, or none of the, however number of notes the trial has segmented out, may be actual notes at all. So this means that if the first step did not manage to detect accurately which segments are actual notes and which are not, whatever models we have will still end up with the wrong pitches. So to find this out, we'll have to look at each trial manually, which of course defeats the purpose of automating this process. So this brings us to Model 5 that I'm presenting today that tries to overcome this problem. I'll be referring to our algorithm henceforth as Model 5 to shorten things. So in the singing app, audio data from participants are saved as frequency values sampled every 500 milliseconds. This shows an example of a 3-note trial. So you can see just loads and loads of numbers. The first step was to specify the pitch range that was allowed for a note. This serves 2 purposes. If a participant is gliding from one note to the next, the segment will not be treated as one single note. Also, Pine, the algorithm for pitch detection, it automatically estimates frequencies for the entire audio, regardless of whether it is clearly pitched or not. So even noise will have pitch values. The unpitched sections, however, usually has widely varying frequency values due to the instability of frequency estimation. So specifying a pitch range also means that the sections that are unpitched are likely to be rejected. The pitch range varies for each trial because when the notes participants are required to sing are further apart, there is a wider pitch variation we have observed. So next, the minimum length with a stable pitch is specified. So segments that is less than that will not be considered. Finally, because frequency is logarithmically related to pitch, all frequency values are converted into MIDI values for computation. With these specifications, Model 5 attempts to find all the segments that satisfy the criteria. So here is an example of a well-produced 6-note trial and the segments that are selected.
Da 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 da.
So there are clearly 6 notes, and Model 5 accurately selected the 6 segments. Here's an example of a trial with a less stable pitch.
Do 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 do.
Model 5 accurately selected them too. Here's an example of a 6-note trial where a participant produced less than 6 notes.
Do, 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 do.
Model 5 also selected the segments accurately. There could be instances where the participant produced more notes than what is required. There could also be instances where Pine incorrectly estimates the frequency of a region that was actually just noise. So for both these types of cases, we determine the most appropriate notes to use for later scoring. Now, how do we do this? So for each trial, there are certain intended notes. We call it the ground truth. MIDI numbers for the ground truth are specified. The intervals or distance between each note of the ground truth is calculated instead of using the absolute pitch value so that it will work regardless of the octave a participant sang in. If more than the right number of notes are selected by Model 5, various combinations are created so that each combination has the right number of notes. And the intervals between these combinations of notes are calculated and compared with the ground truth. The combination with the intervals closest to that of the ground truth are selected. Here's an example of a trial where this segment circled in green is also a potential note segment. In actual fact, this portion is just noise, but which pi-in has forcibly estimated frequency on. So when interval distances are compared, this segment was correctly rejected. So overall, how accurate is Model 5? We performed a correlation of a set of data for the pitches derived from Model 5 with pitches that have been manually annotated and obtained with PROT. There is a slight difference in frequency estimation by pi-in and PROT because of the slightly different algorithms they use for pitch estimation. But this slight difference shouldn't be a cause of too much concern in terms of the things that we are interested for assessing singing here. And Model 5 does this automatically in a few seconds, what a human annotator does manually over many hours. So where do we go from here? MAS-21 has been used in conjunction with various studies in our lab. Of relevance here is a study with participants in a choir for people with Parkinson's disease that tries to see if choir singing slows down degeneration of their vocal control. Margaret has presented some parts of this research in the poster session earlier on. We also have used this for studies exploring gender and cultural attitudes to singing and ages of music acquisition and so on. With all these different users, we need a way of scoring participants' responses after we obtain the note segments from their audio data. So currently we have this scoring schema, but a variety of other things could also be considered depending on which aspect of singing we are interested to examine. First, we compute the scores using pitch chroma rather than absolute pitches. This is because people have different vocal ranges, and what we want to find out is the pitch chroma and ignore what octave they are singing in. For the single note trials, we simply score the distance from the correct pitch chroma. For multi-note trials, we take their distance from the correct pitch chroma together with accuracy of their intervals between notes. This is the weight we have currently assigned for relative and absolute accuracy. So 50% each for 2-note trials, 1/3 for absolute and 2/3 for relative in 3-note trials, and so on. However, this can be easily adjusted based on whatever is needed and whatever one feels is more important in that particular task. In addition, we can also assess vocal control by calculating the number of inflection points as well as the variance in pitch to give an indication of pitch stability. To give an example of how scores on MAS-21 may be related to measures of music sophistication, we calculated the correlations of scores of the Go MSI with singing scores for 75 participants. The singing scores correlate with 5 of the 6 measures. So in conclusion, Model 5 can be used to automatically and accurately detect note segments in participants' singing data. This is not a replacement for the available pitch estimation and note segmentation algorithms that are out there for audio transcription, because our implementation is simply to provide a solution for this very specific type of data that we collect. The battery of tests in MAS-21 can be modified to be used in different settings for different populations to assess singing skills and vocal control. We also have different options for scoring depending on the things we want to assess. And we're working on developing other types of assessments or tasks for different aspects of the singing voice, such as timbre quality, potentially expanding the range of users for MAS-21. So here are our references, and we would like to thank these people and organizations for their support of our project and everyone in the Music Cognition Lab at UPEI. If you have any questions for us, you can reach us at this email address. Thank you.
Lena. Thank you, Lena. Questions from the room or online? I will start. Lena, if there's someone who wants to embrace the test and incorporate it into their battery, what do you recommend? How would you proceed? Um, um, is
Contact us.
You're shaking your head, so I'll
No,
just go ahead.
contact us. Sorry? Can you hear me?
Simple as that. And
Well, to give you the link to the test
yeah,
that we're using.
yeah,
But a couple of, they have two versions of the test. But
yeah.
we could send a link.
But isn't there like two aspects, like the test itself and then the analysis pipeline? Yes.
So I'm not certain that Lena will be able to hear and answer, but
She can hear.
then she could answer.
Go ahead, Lena.
Yes, so there is the test of this 21 different tasks, and then there is also this algorithm. So what happens is that right now the audio data is being saved as RDS file as well as the audio recording. And then you will use this algorithm and do it, afterwards. But it could be incorporated into the test. We will just have to modify the test itself a little bit.
The one to analyze the data relatively quickly. Okay. But
Okay, thank you. Yeah, it seems like a valuable resource to different groups potentially. Any other, it's because a lot of us are interested in these singing gains in addition to the other communication outcomes. Um,
Thanks for this work. I'm certainly very interested in that. We talked about. Um, yes, so in addition to the algorithm, the actual test, I was wondering how long it take to administer a test with sufficient data so that you can analyze and come up with the valid scores, I would say, of singing abilities.
Do you mean how long it takes for a participant to complete the test, or do you mean how long it takes for us after we get the data from the participants to get this scores and pitch values?
Usually, I'm more concerned about the patient or participant time than our time as a researcher.
Uh, Maybe Dr. Cohen would be able to answer that part about how long a participant usually takes.
current test would be about 15 minutes, but there's maybe 5 minutes before that, just getting everything adjusted properly, making sure their voice is being picked up, that kind of thing. Yeah. But you can make the test as long or as short as you want, but not with ease at the moment. Like it would, but it can be done. Like for Margaret's study, we added a new piece where they had to make up a song, and so it can be done. We also added the sing. Margaret, you were there. Do you want to say anything about the couple of tests that you added for the Parkinson? The
Sure.
Chinnamarun.
We asked them to read the.
Sorry.
Right, sorry.
Thanks. We asked them to read the grandfather paragraph. We asked them to sing the highest and lowest note that they could, as well as hold one note for as long as they could of any pitch. Yeah, and then make up an ending to a short melody.
And if you're wondering why is this in the Parkinson session, the work that Margaret presented in her poster, I don't know if you got to it, utilized some of this battery, and they did find some changes that tracked with time spent singing and time lived with Parkinson's. I passed. I didn't fail. Margaret nodded. Okay. Okay. So we'll stop there.